So in the last video, we had a discussion about carbon, and we said that carbon's pretty special, on the periodic table at least, and that's because he's got the location. He is in a prime spot to give you a plus or minus 4 as far as charges go, which really give it an ideal situation in terms of bonding. And we also said that it was super tiny and small compared to the rest of the atoms in that column. Okay, so we need to further our knowledge of general chemistry a little bit. And now is where we'll get to the nitty-gritty. Before I do that, though, let's just go ahead and have a summary of the difference between organic and inorganic, just to touch base with this one more time. All right, so first, on the column to the left, you're going to see the properties of an organic molecule. Look, organic right up here at the top. So here they are. Number 1, bonding is entirely covalent. All right, now, we have not really talked about the definition of covalent, but we will. Just give me some time. We'll review some of these terms that you need to know in the general chemistry side of the house. Organics, well, those compounds can be gases, they can be liquids, or they can be solids. And you'll see that throughout the laboratory experience of the class. Gases, liquids, and solids are very common. You'll also see it in lecture, because we'll talk about properties and states of matter when we're talking about reactions. Next, most are insoluble. Insoluble, of course, means that it does not dissolve in water. Organics and water do not mix. Think of oil and water. Oil is an organic molecule. Oil and water don't mix, and most of the organics that we use in a laboratory will not be aqueous as far as solvents go. Again, completely different than general chemistry. Next, most are soluble in organic solvents. All right, well, what is an example of an organic solvent? Well, that can be something like ethanol, which is your good old-fashioned drinking alcohol, okay? Or it could be acetone, which is basically the old-fashioned fingernail polish remover. Some people still use it for that purpose. Next, they do not conduct any electricity at all. That's just a common property of organic. And again, these are general statements. There's always exceptions. And finally, the reactions are very slow. Okay? So that is a general summary of what we would classify as organic. And again, this class is focused on organic, and these are the properties that we're going to be talking about. Over on the right-hand side, these are the inorganic side of the house. This is your general chemistry kind of thing that you've become accustomed to maybe over the past year, or at least 2 semesters worth of it. Most of them have ionic bonds. Again, we'll talk about the differences later. Most of them are solids. It seems like every time that you did a lab experiment, you were using solids almost every single time. Well, that's because it was inorganic, and that's the side of the house that you were playing on. Many are soluble in water, so general chemistry loves to use aqueous solvents and water as a solvent. Organic chemistry, rarely. That's a big difference. Next, almost all are insoluble in organic solvents. Almost all of them will be insoluble in typical organic solvents. Again, oil and water do not mix. They do conduct electricity. That was probably a property that you studied in general chemistry, voltaic cells and electrochemistry. If not, I'm sorry. And then most of the reactions are very fast. And that's very good, especially if you're teaching chemistry lab and you want the lab over with in an hour. Well, that's not going to happen in organic. I hate to break it to you. These reactions are very slow, which means a 3-hour lab period really is a 3-hour lab period. So now that you have become more familiar with the field of organic chemistry, I told you and I promised you that this lecture was going to be a general chemistry review, and we haven't done any review of general chemistry at this point, but now's our time. So I'm going to go back to basics. If you've ever watched the Food Network channel and looked at Anna Garden, you know what Back to Basics is. She has a Back to Basics cooking show, and she teaches you how to make lobster bisque in Back to Basics. So I hope that I'm not telling you how to make lobster bisque. Hopefully I am talking to you about basics, and hopefully all of this information is very common to you at this point. So don't let me be Anna. If I am Anna, you need to let me know. All right? So we're first going to talk about atoms. And when we talk about atoms, we're going to be talking about parts of an atom. And there are 3 major parts. There's actually over 20-some actual parts of an atom at this point, and that list continues to grow, and it makes bigger and bigger and bigger, but we focus on 3, and those parts are typically abbreviated as a P plus, and an N, and an E minus. All right, so the P plus is a proton, and a proton, of course, is a positive charge. That's why there's a plus up at the top. If I give you that question on a test and you miss it, well, you know, we need to have a talk. All right. N is going to be a neutron. All right. So a neutron actually is neutral. That's why we do not write a symbol up here in the top as a superscript. Some people do write a 0 there, but I just think it's a little bit confusing, so I'll leave it off. But if you put it on there, no big deal. Some people do. E, of course, stands for electron. And electrons, as you learned in general chemistry, hopefully, were negative. All right, so those are the 3 major parts of an atom, and these are what we call the subatomic particles. Now, the reason we call them subatomic is I see the word atom. So atom is the thing that we're studying, and sub means below. So this is below the atom, which means part of an atom in a way. So these are 3 parts of the atom, or subatomic particles of an atom. One is layman term, the other one makes you sound a little smart. So use subatomic when you can, because that's what it means. All right, so in the atom, let's talk about structure. Well, here's my awful drawing of a circle that represents an atom. You have to think of 3 dimensions here. So think of a sphere, not a circle. So think of something like a tennis ball. In the center of that ball, we have something that we call the nucleus. And that's the nucleus of the atom. And that nucleus is what we would refer to as the core. Well, there are 2 particles that are located at this nucleus. Those particles are the protons, which are P+, and the neutrons in the nucleus inside of the center. All of these are basically mushed up together into a very dense core that we call the atom. All right, now here are the problem kids. Those are the electrons. All right, those electrons, at one point in time, we just thought, they could just be anywhere they want to be. Okay, they're rebellious. They're going to tell you what they want to do. But over time, we quickly understood that that wasn't necessarily the case. These electrons cannot be wherever they just want to be. And we'll talk about some of these rules that are out there for those. But in this drawing, I'm just going to kind of randomly put them in here. All right, so those electrons, I've randomly put them in there to give you the idea that they are scattered. Protons are all together in the core. Neutrons are all together in the core. The electrons are scattered throughout the entire atom. That's one of the major differences here. Okay? So, I'm telling you now, this will be a test question. See, look at that. I'm not a bad, horrible instructor, am I? I'm telling you what's going to be on the test. the test that you will complete by hand. This will be one of the questions. What are the 3 subatomic particles? Name them. Give me the charges of those and tell me where they're located. And if you can replicate this, you get full credit for the question. Look at there. No one said this class had to be difficult, did they? All right, so this nucleus houses 2 of the subatomic particles. The electrons are then scattered throughout the rest of the atom. And that rest of the atom is mainly empty space. You know, there was an analogy that someone used at one point in time, and I really like that analogy. And what it said is, imagine a football field, folks. A football field. And that football field represents the atom. That football field will be the space that the electrons will occupy. Now, they just can't run wherever they want to run in the football field. Okay, there's guidelines. There's strict guidelines in place. This is where you got to be. You can't be anywhere you want. And we'll talk about some of those rules. But the football field is the atom. Now, imagine someone with an ink pen. And that person walks in center field, and they hold that ink pen up. The tip of that pen, the tip of the pen, represents the nucleus. Now you see the picture. Now you see the vast empty space that atoms take up, right? So the protons and the neutrons are loaded on the tip of that pen out in center field, 50-yard line. And the rest of the football field is empty space. And that empty space is where these electrons will be. I think that will give you a perspective, maybe a different type of perspective than you've never had with an atom before. So these atoms, they are voids. You're made up of atoms, so therefore you're made up of empty space. That's just the way it is. But these voids really play a major role, because that's where all of these electrons are going to be located. Folks, if that's where the electrons are going to be located, that's where they're going to be moving around. That's where they're going to be doing stuff. And that area is going to be very important to us if we want to understand how reactions are going to happen, how these atoms react with each other, how they interact with each other, how they form products, how the reagents come together and move things around, like in that volar mechanism that I showed. That area is super, super important. Now, I'm going to combo it a little bit. I'm going to add to the story. There is a moment in time where these electrons do run around and they play. All right? And sometimes they get a little worked up. Imagine kids eating too much chocolate. Okay, they're going to go into a sugar rush. And electrons kind of do the same thing sometimes. And when they get on their sugar kick, we can't really control them as well. And they do some things that a normal electron would not do. And there is a chance that if you turn these kids loose in that football field, one of them could hop over the fence and run away. And then we call the police. But in the world of chemistry, we don't call the police. We just accept the fact that they're going to run away. And we say, oh, well, if they come back, they come back. If they don't, they don't. I'm not saying parents should be that way, but maybe some wish they were that way. But these electrons can leave. If those electrons leave, this is a negative charge that they're going to take with them. So that negative charge is going to leave as well. And then no longer do you have a balanced atom anymore. You now have a charged atom. That charged atom, if it loses an electron, it loses a negative, so therefore it becomes a positive charged atom. But there could be a nearby football field with more kids in that football field. That's another atom. And that electron that escaped this football field, it could maybe go to the next football field and say, I want to play here. These kids look like better friends. I want to hang out with these guys. They're cooler. And electrons can come into the football field as well. If I gain an electron, I gain a negative charge, which means that that atom becomes negative. All right? If I lose the negative, the atom has one less, so therefore it's positive. If I gain the electron, the atom now has an extra negative, so therefore overall it is negative. If this happens, this charged atom has a term, and that term is called an ion. Now, we'll talk a little bit more about ions later, but this is your first encounter with me on what an ion is supposed to be. All right? Most of the mass, like we said before, was located in the nucleus. That's where the protons are. That's where the neutrons are. The electrons, they're like little gnats. I know I called them kids, but now I'm going to call them gnats. And maybe for some of you, you might think of the two the same. I don't, but you might. Okay, well, the reason I call them gnats is because the electrons, they weigh very, very little. 1/1837 compared to a neutron of 1 and a proton of 1. And these are in what we call atomic mass units. These are not in grams, folks. All right, this is not 1 gram, 1/1837th gram. This is AMU. Atoms are extremely tiny, and gram is extremely big for a unit when we talk about mass of an atom or a proton or a neutron or electron. So what we do is that we get out of gram, and we can measure these in grams, but they will have like a 0.000000000 all the way down, okay? Well, we convert that over to what we call an atomic mass unit that allows us to clean this number up a little bit better to give us a whole number. That's why we do it. We make it easy. We try to make it easy for you. And we say protons are 1 AMU. Neutrons are 1 atomic mass unit. And electrons are 1/1837 atomic mass unit. That means it takes almost 2,000 electrons to give you the weight or the mass of 1 neutron, or almost 2,000 electrons to give you the mass of 1 proton. So, nucleus has the majority of the mass in the center. All of these little kids, they're like little gnats that fly around, and they can come and go as they please, and they're super, super tiny, and they weigh very, very little. It's kind of weird when you think about it. When you actually take the time and think about how the structure of the atom is set, at least what we know, then this is a very strange setup. But this setup allows the atoms to begin to react in the proper way. And we will come to learn and appreciate everything that these particles do. And out of the three, folks, the gnats are the most important. Yeah, we can talk about protons. We can talk about neutrons. We can go through and talk an entire field of chemistry on those. But the driving force in organic especially is the electrons. We could care less about the nucleus. We could care less about the protons and the neutrons on the inside. We are rarely going to look at those. What we are going to study are the gnats of the atom, the things that come and go, the things that weigh very, very little, because those are the most important pieces to the entire thing. Again, very strange concept here. But this is what your general chemistry class should have reviewed with you or should have taught you during those semesters that you were there. So in the next video, we'll pick up from this. We'll continue on with our description of subatomic particles and the structure of the atom and some more things that should be a refresher for this series of lecture videos.